Hi. So now we want to look at two very interesting notebooks, which is one where we learn to do mathematical reasoning from a base model, and two where we learn to do tool calling. And in the mathematical reasoning, we compare SFT to GRPO, and in the tool calling, we compare SFT to DPO. Okay, so let's go with the first one, which is the mathematical reasoning. So what we want to do is this. So I'm going to read it out, read out the code, explain. Most of it is self-explainable, but just for a little bit of hand-holding if you need it. So this notebook compares two fine-tuning approaches for teaching mathematical reasoning. One, SFT, supervised fine-tuning. It learns directly from correct solutions, simple and fast training, may memorize rather than generalize. And we've covered all this in the videos earlier. And the second is GRPO, the DeepSeek moment, right? There they use reinforcement learning approach with custom reward functions, learns from multiple generations, and their relative quality can optimize for specific criteria, format plus accuracy. And the data set we use is also downloaded from Hugging Face. It's called the Numina Math TIR, mathematical problems with step-by-step solutions. The model we use is Qwen2 0.5B instruct model. It's very small but capable and already instruction fine-tuned. What does it mean instruction fine-tuned? Means already SFT has been done. Right? And another thing to note is, what do I mean by custom reward functions? Well, as we discussed in the video, the reward function for math is simple. You need to have the correct answer, and an additional thing we add is, okay, we need to see think tags, right? So we start by installing dependencies. We need TRL, which is the transformer reinforcement learning library from Hugging Face. And it provides us with these two classes that we want, GRPO trainer and SFT trainer. We use PEFT, which is another library which helps us in parameter efficient fine tuning, where we use LoRa from there. Then we have our math verify library for verifying mathematical expressions and LaTeX. We have transformers, the core library for loading models, which we have seen earlier. We use the datasets library, and we use the accelerate library if we want to distribute training across multiple GPUs. So we do a pip install of all these dependencies, and they get installed. And then we do this Hugging Face authentication so that we are able to download gated models if needed, push train models to our own account, and track experiments. And I recommend we all get comfortable with Hugging Face, because Hugging Face is not going anywhere. And once we do this notebook login, we see that, okay, we are able to log in properly. And then we do the dataset loading. So we want to load this Numina Math TIR dataset that has the problem, the solution, and the messages. The problem is the mathematical question itself. The solution is detailed step-by-step solution with Python code, and the messages are pre-formatted conversion format. And we use only 5% of the data set for fast experimentation. You can increase it if you want to actually fine-tune the model for production. But for this didactic example, for us to get a feel for it, 5% is sufficient. So we import load dataset function from the datasets library. We call the dataset ID to be this AIMO Numina Math -TIR, and then we load 5% of the dataset by giving it into this split. So we call load dataset with this split of 5% and 5%. And then we look at the examples that we've loaded. So we see that we've loaded 3,622 train examples here, and test examples 5. And then we inspect the dataset structure, and this is good practice. You should always do it. We want to look at what our dataset looks like. So a little bit, if we kind of print it out, it looks like in the problem it's written, what is the coefficient of x square y to the power 6 in the expression fraction of 3 by 5x minus fraction of y by 2 to the power 8. Express your answer as a common fraction, etc. And the solution preview is to determine the coefficient of this in the expansion of this. We can use the binomial theorem and so on. And then the binomial theorem states that a plus b to the power n is sum of k equal to 0 to n of the binomial n comma k and a to the power n minus k, b to the power k. So this is just the formula, and then in this case we apply it here. So this is what the data set looks like. I recommend you spend more time with data. Look at what data actually looks like. Now we convert this raw data into this conversation format that is expected by the model. So the target format that we want, that the base Quen model was already trained on, and thus we need to follow that, is system prompt explains the expected output format, user provides the math problem, and the assistant responds with this think, reasoning think, and then answer, right? So in think tags there has to be the reasoning, and in the answer tag has to be the final answer. And the structure format allows us to verify the model, that the model follows these instructions, and also that it kind of extracts and verifies the final answer. So the system prompt that defines the expected output format, and the model should wrap the reasoning in think tags and answer in this answer tag, is given by the system prompt. And the system prompt essentially says a conversation between user and assistant. The user asks a question and the assistant solves it. The assistant first thinks about the reasoning process in the mind and then provides the answer, user with the answer. The reasoning process and the answers are enclosed with the think tags and the answer tags respectively. That is think, reasoning process, and that is think, reasoning process here slash think, answer here slash answer. And then we make a conversation example from the data set, right? So we say, we convert the dataset example into a conversation format, creates a prompt with system message defining the output format, user message containing the actual math problem that we get from the dataset, from the Numina dataset, and the arguments are example, the dataset row with the problem field, and returns dictionary with the prompt key containing the list of messages, right? So the prompt is role system, content system prompt. System prompt is what we defined earlier, and then role user, content is the example, right? And then example is passed into this. Then we apply the conversion to both the data set. We say that the columns that we want to keep are the prompt and the solution, and then we massage it, we remove all the other columns, we then remove columns from our trained data set and test data set, and only keep the columns that we're interested in. So the columns that we keep and that we're interested in are the solution and the prompt. And then the converted prompt format is content, conversation between the user and assistant. We've already looked at this, and so on. So this is what the this thing looks like. So it's exactly that. And now the content, and then this is the user content, right? This is what the problem will look like. So we have formatted our question, our mathematical data set, into this question answer format that this Quen 2.0 model was already trained on using SFT. Okay. Then we load the base model. We set the DPU, device map to be auto, because we don't know if you have a GPU or not. You can also run it on the CPU, will be very slow. And this is for automatic GPU placement. We import auto model for causal LM from transformers, and also auto tokenizer. We say that the model ID is this, because this is what we have downloaded and this is where we have kept our model. And then we create this model, we load this model, and then we also create this tokenizer, and then we print that we have loaded this model. Our CUDA device, we have a CUDA, and the CUDA device number is 0, and we are using bfloat16. So we usually use bfloat16 with diffusion models and also with LLMs. We then configure our LoRa adapters. So the LoRa adapters create these it makes our fine tuning efficient. We don't update all the parameters. We create these additional parameters, low rank approximations, which we update. So these are much lower in comparison to the entire number of parameters. And then from PEFT, from this parameter efficient fine tuning, we import the LoRa config and the get PFT model. In the LoRa config, we say that you're using the causal LM because it's a causal language modeling task. We use the rank of LoRa to be 8, the LoRa alpha parameter, hyperparameter to be 32, the LoRa dropout to be 0.1, and the attention layers to adapt. So what do we want to adapt? We want to adapt the Q projection matrices and the V projection matrix, right? So this is where we add our Q LoRa parameters, the LoRa parameters. And then we get the model. So we give the original model to this, and then we get the adapted model. So this is a model where it has additional number of parameters, the LoRa parameters, and then we look at, how many parameters did it originally have. So originally it had almost 500, so this is a 0.5B model. So almost 500 million parameters it had. And then we added only 500,000 additional parameters. So the trainable number of parameters are less than, it's almost like 0.1%. So 0. It's just 0.1%, not even 1%. So 0.0001 times the original number of parameters. And now we define the reward function. So GRPO uses reward function, and the reward function that we use are, does it follow the required structure? Does it answer in these think and answer tags? So that is one reward because we explicitly mentioned it in our prompt. So it should adhere to that. It would obey that. If it doesn't, we penalize it. We give it a bad reward. And so we give it a good reward 1.0 if it has these two tags and 0 otherwise. And then the accuracy, right? So we compares the ground truth using the math verify, and it handles the LaTeX and numerical equivalence. So we format reward. So this is where the reward function checks if the completion, and here it's simply regex, and this regex is basically just checking if it has those think and answer tags, and this accuracy basically checks if the answer is accurate. And then we configure GRPO, and configuring GRPO is very easy because you say, okay, how many number of generations do we want? In the video we said 8. Here we say 4. Max completion length, maximum tokens per generation. So short for speed because we don't want more than 64 tokens as output. So we say 64. Gradient accumulation step. So effective batch size, the denominator of 1 by S, that S is equal to 16 here. And then learning rate of 1e minus 5. So conservative LR for stability. We can slightly go higher, but we don't want to. And as you remember, GRPO works by taking the same prompt, getting multiple answers, averaging over it to get the value function, getting the reward for each of those answers, subtracting the value, and then using that as a multiplier to the cross entropy, right? And then we use these rewards to update the policy. Policy is just another word for the LLM itself in the RL lingo. And now we set up the GRPO config. The config has these hyperparameters, and we say that, okay, our GRPO configuration is this, the output model name is this, so we use the base and then we call it test, generations per prompt, max completion length, and then we simply, instantiate this trainer and we just call train, right? So we start the training time and then we say, okay, we are now gonna train, and then training starts, right? So GRPO trainer and trainer.train. That's it. That's all we have to do. And then later we do a bunch of evaluations, etc., so that we know how good or bad they are. And this is where a lot of code actually gets written. But this is all that there is in this notebook, right? So now it's all yours, and go play with it, fine tune it on other data sets, get a hang of Hugging Face, and of course you'll have access to all these notebooks. But the message here is that, okay, it's really simple, and there's nothing difficult in fine tuning LLMs, be it SFT, be it RL. And pre-training is even easier, but it's a lot of compute needed, and you and I probably cannot do it just by ourselves unless we have tens of millions of dollars.